Good morning, everyone. It's Monday, May 11th. We have 2 weeks left of digital learning, 6 lessons, 6 short quizzes, and you are done with science for the year. All right, so I really need you to focus, set aside the 15 or 20 minutes a day that you need in order to do very well and to learn what you need to learn on these units so that we can finish the year strong. All right, so today we are going to start the unit on the Sun, Earth, and Moon system. And if I don't forget, I will have this chapter already sent to you by the time that you watch this video so that you can follow along with me and see exactly what I see on my screen. All right, so here is what we're going to do. We are going to look today at pretty much information about the Earth because the sun, the moon, and the Earth together show us different phenomena that we're going to discuss tomorrow and the next day. And so, first, we need to kind of understand the dimensions and characteristics of the Earth that help to make this happen. All right, so getting started, we're going to look at some of the properties of the Earth. And the first property that we need to look at is the shape of the Earth. I know some of you are on YouTube or Snapface or Instabook or whatever it is you guys are on, and you still hear about flat earthers, right? That the Earth is flat. I got news for you. The Earth is not flat. All right. The Earth is a sphere, which is a round three-dimensional object. All right. Uh, we say it's it's round or it's a circle. It's not 100% true, but it's really darn close, and I'll show you that in just a second. But I'm going to show you first how we know the Earth is round. Yes, none of us have been up high enough away from the Earth to actually see that the Earth is a sphere, um, but some astronauts have. We've got satellites that are up high enough to take pictures down here and show us that the Earth is round. But long before that, we're talking 350 BC, so almost, 2,500 years ago, people had this figured out. All right, and I'm going to show you a couple of examples of how they did that. First, sailing ships. And if you look at these three pictures, what sailors would notice, even and this works best on a calm day, all right, but they would notice that as a ship was approaching them and they looked way out on the horizon, the first thing that they could see was the top of the ship. It wasn't just a miniature, the whole ship just way far away. They could see the top of the ship first. And as it got closer, then they could see more and more of the ship. And eventually they could see the entire ship. And what that shows is that that ship actually was sailing over a curvature in the earth. It was lower, so it was here, so all you could see is the top. And then as it got higher, you could see the middle. And as it got even with you, then you could see the entire thing. All right, so that was the first clue. Um, there were plenty of other pieces of information that allowed people to know that the Earth was round. One of them is going to be a big focus, I believe, tomorrow, and that is lunar eclipses, where we can actually see the shadow of the Earth projected onto the moon, and you can see the curved edge of the Earth on one side, and then a couple hours later, the curved edge of the Earth on the other side. All right. So the Earth is round. It's a sphere. Not perfectly round, but it's a sphere. All right. Some other characteristics of the Earth that are important for this unit are the fact that the Earth rotates, that it spins on an axis. And if you look at the picture here, there really is not a metal rod that runs from the South Pole through the North Pole. All right. This is an imaginary line that the Earth rotates around. So the Earth spins. All right. Now, these are some interesting numbers in this table. All right. The diameter from pole to pole, so from South Pole to North Pole, is this number, 12,714. The diameter at the equator, so going this direction, is 12,756. So you can see it's a little wider at the center than it is from top to bottom. So the shape of the Earth is like taking a beach ball, holding your hand on the top and the bottom, and slightly squeezing. The middle sticks out just a tiny bit, all right? And that is a more accurate representation of the shape of the Earth, all right? It's pretty darn close to round, but just a little bit wider from side to side than it is from pole to pole, all right? You can also see the circumference and the mass. This is a scientific formula that scientists use to figure out, like, if you stuck this thing on a scale, what would the numbers read? They're able to figure out the average density, 5.52. Remember, density is greater than 1 would sink in water. So if you put the Earth in water, it would sink. All right. That's not true of all the planets, by the way. Hopefully, you realize that those gas giants, their densities are going to be quite a bit less because gas is less dense. So there are some planets that actually, if you had a swimming pool big enough, would float. Average distance to the sun, 149.6 million kilometers, about 93 million miles, although that varies because the orbit of the Earth around the sun is not a circle. If it was a circle, it would be the same distance from the sun at all times, but it isn't. And the orbit's actually a sphere, so sometimes the Earth is closer, sometimes the Earth is farther away from the sun. Period of rotation, that means how long does it take for the Earth to spin around once, to rotate once? And we call that a day. And we're pretty programmed to know that a day is 24 hours. However, the actual amount of time that it takes to rotate or spin around once is 23 hours and 56 minutes. So there are 4 minutes in there that are unaccounted for, kind of. I'll teach you about that in a second. And then period of revolution, that means how long does it take for the Earth to make a lap around the sun, to make one orbit around the sun? 365 days is what we know as a calendar year. But you can see that it takes 365 plus 6 hours plus 9 minutes. So again, in our calendars, in our system of time, we have to account for those differences, which I will teach you about down the road. Let's address this period of rotation. 23 hours and 56 minutes for one day, for it to spin around once. What happens to those other 4 minutes? I realize that on the whiteboard of science here behind me, it might be a little bit difficult to see, but we have the Earth here, and over the course of its rotating one time for one day, the Earth is not going to remain in the same place because it's orbiting the sun. So when it starts its 24-hour cycle, its 23 hours and 56 minute cycle, it's still moving. And so what happens is it actually takes another 4 minutes for the Earth to line back up the way that it was at the beginning of the previous day because it's moving around the sun. So there's where those extra 4 minutes come in our day. All right, it takes 2356 to spin around. It takes 4 more minutes to make it appear that way because the Earth is moving, which gets us our 24-hour day. I know, a little bit hard to visualize. Look up a video, type it into Google. There's all kinds of fun stuff on there. All right. Let's look at some other facts. The Earth has a magnetic field, all right? And it has magnetic poles. If you were to follow an old compass, that's got the needle that's always pointing to the north, it would take you to the magnetic North Pole, which is not in the same location as where Santa Claus lives. It's not the geographic North Pole. Our magnetic field changes over time. In fact, right now it's moving further away from northern Canada and moving towards Russia, all right, which causes all of our GPSs to have to be updated fairly regularly because the actual magnetic North Pole is in a different location than it was the previous year, and so on and so forth. All right. So we've got this magnetic field and these magnetic axes, the magnetic north and south pole. Now, what causes the changing seasons? All right. If I had to say the answer in one word, it would be this: tilt. The tilt of the earth causes the seasons. All right. We live in the northern hemisphere, so when the northern hemisphere is tilted towards the sun, we have the most direct energy, and it's summer. When the northern hemisphere is tilted away from the sun, we have less solar energy, and it's winter. All right. So the changing of the seasons is 100% about the tilt of the earth. Now, as we go through the orbit around the sun, we are also closer and farther away from the sun at different times. However, they do not correspond with our seasons. We are actually closest to the sun in January when it's winter here. We're farthest away from the sun in June when it is summer here. All right, so it's not about the distance away from the sun that causes seasons, it's about the tilt. And here in the picture, you can see the northern hemisphere tilted towards the sun. We get more direct sunlight. Wisconsin's about right here, and that's our summer. All right, the tilt of that axis is about 23.5 degrees. That does change slightly over about a 50,000 year period from in the 21.5 to 24.5. So sometimes it's tilted a little more, a little less, and that's going to certainly affect seasons and temperature here. The average is about 23.5 degrees, the tilt of the earth. All right. Now, there are 4 specific dates that correspond to the Earth's location around the sun in its orbit. 2 of them are the solstices. All right. We have the summer solstice and the winter solstice. We actually call those days the first day of summer and the first day of spring. The summer solstice would be illustrated right here. It is the point in our orbit where the North Pole is tilted closest towards the sun. All right. So when the Earth is on its tilted on its axis and it's pointing the most directly towards the sun, we call that the summer solstice. It's the first day of summer. Now, as we continue along, notice the tilt of the Earth doesn't change. But when we get alongside the sun over here, we call this an equinox. And we have the equinoxes are in the spring and the fall, right? So first day, so if this is summer, first day of summer, and we continue on in our orbit around the sun, the next season that we have is fall. So this would illustrate the fall equinox, and this is a day where, well, equinox has the root word equal, where there are approximately 12 hours of sunlight and 12 hours of darkness on these equinox days. All right. Now, excuse me, we continue on in our orbit around the sun to get to the opposite side where we are tilted away from the sun. This would be the winter solstice, the first day of winter. And we continue on in our orbit around the sun, and we are back to spring, the spring solstice. All right, again on this day, the spring equinox, we would have an equal number of daylight hours and nighttime hours. So summer, fall, winter, spring. All right, summer and winter are the solstices, and fall and spring are the equinoxes. I know, some crazy new vocab terms that I need you to understand today. All right. That's it for chapter 1. All right. There will be a short quiz that goes along with this. Remember, your grade for the week is 100% based on you taking these quizzes. So hopefully you watch the lesson and you do the best that you can on these quizzes. If you need my help, email bswitz@nfdlschools.org. Hit me up on Google Messenger, request a Google Meet. Whatever it takes, I'm here to help you. All right. So, with that said, do your best on the quiz, and I will be talking to you tomorrow. Have a great day.